Hi everyone, I'm Farad. In this session I'm talking about flow meter in hydraulic lab 1. So heat transfers from higher temperature to lower temperature. If we want to translate the same concept for water, what would be replaced here? So water travels from here, from higher to lower. It could be elevation, it could be pressure, and also it could be velocity. So simply you can send water from lower elevation to a higher elevation just by pressure, pumping the water to the higher land. And water simply can flow from higher elevation to lower elevation, and also you can send water from higher velocity to lower by terms of velocity. But in terms of a comprehensive approach, all these together translate in the terms called water head. So water travels from higher head to lower head. These three components consist the three terms of Bernoulli's equation. If you have a closer look to a Bernoulli equation, so Bernoulli's equation, it says Z1 plus P1 over gamma plus velocity 1 to the power of 2 over 2g is equal to the same terms for second cross section, Z2 plus P2 over gamma plus V2 to the power of 2 over 2g. In Bernoulli's equation, these terms stand for height from a base, a specific base. This term called S, equivalent height of pressure, and this term called similarly equivalent height of velocity. The reason they called equivalent height of pressure or equivalent height of velocity is because the unit of all these three should be in something in meter, feet, or inch, whatever it is in terms of a length, either in SI unit or British unit. So if we take a closer look to what's happening in Bernoulli's equation in terms of dimensionless analysis, to see how to reach to the same unit for all three terms of Bernoulli's equation. So by a bit of dimensionless analysis, which we show length by L, L stands for length, time with T, and mass with M. We do know F force is mass times acceleration. Mass is in M and A is in meter per square seconds. So the dimension for force would be M, capital M, times meter in length, it's in length and stand with L, capital L, times T to negative 2 because it's in the numerator. We know pressure is force applied on an area, so it would be, dimension would be the same, replacing from here mass times L times T to negative 2, and area would be L2. Area to the power of length to the power of 2 would be area, and it would be M L minus 1 T minus 2. If I call this equation 1, and from the other side gamma is equal to rho times G, density times gravity acceleration. For rho, we know rho is mass over volume, so it would be M over L to power of 3, and we can show it like M L to the negative 3. And G is in terms of, again, meter, for example, over square seconds, so it's L times T to negative 2. If we have them together in terms of dimensionless analysis, it's M L to negative 3 times L times T to negative 2. So it would be M L minus 2 times T minus 2. If I call this equation 2, and again I apply this to second term of Bernoulli equation, which was P over gamma. So it's simply dimension analysis of 1 over 2. So the dimensionless analysis would be M L minus 1 T minus 2 divided by M times L to negative 2 T to negative 2. If we look at this equation, M cancel out with this M, T2 times cancel out with this T to negative 2, and we left by L to negative 1 in the denominator. it comes up and be left with dimension of L. So P over gamma, it's in the unit of length. That's why we call it equivalent height of pressure. If you do the same thing for the third term of Bernoulli equation, which is V1 to the power of 2 over 2G, again you reach to dimension of L, which is again, this time we call it equivalent height of velocity. These three components are the major contributor to Bernoulli equation. In next section we are going to relate the same concept of Bernoulli equation by applying at the same time with continuity equation to know how to measure the flow.